Right. Good evening and hello. I'm going to be streaming out to an audience of nobody tonight because we missed one of our class meetings Wednesday for the hurricane closure. I'm going to try to keep this short, but sometimes when there's nobody here, I can tend to be a little long-winded. So I apologize in advance if this is a little long. Remember that you don't have to watch these things all in one go. You can pause them and come back to them. In general, every time I scroll down on my OneNote to a new problem, you can feel free to go ahead and take a break. Try to keep it to about 10 to 15 minutes each, but there's 5 or 6 of these, so this might last about an hour or so. The end of Module 1, or Module A, in my open math is going to deal with quadratic equations and quadratic expressions. These are probably what you need the most review on. I know that assignments 1 and 2 were about fractions and exponents and linear equations. Most people don't need a lot of intensive review of those things, although I am available via email and the discussion boards in my open math if you do need a little bit more review on that stuff. So don't feel bad about that. I'd like to spend most of the time today talking about quadratic expressions and quadratic equations. What we mean when we say quadratic, the word quadratic, it means I've got this second power here. Any equation or any expression which contains that squared on a variable, I would call quadratic. And as a class of problems and as a class of expressions, quadratics have a lot of nice properties to them. We'll see in a little bit that they're pretty much fully solvable. They are a very well-studied case. But when it comes to equations, quadratic equations are a little bit different because unlike linear equations, quadratic equations may have more than one solution. And I've written this very simple one here, x squared equals 4, because you can probably see the solution is 2, because 2 squared equals 4. That's true. But x equals 2 is a solution. That's not the only solution. X equals negative 2 is also a solution. Don't forget that when we have parentheses and exponents, negative 2 with the parentheses squared is not the same as negative 2 without the parentheses squared. Negative 2 squared is equal to 4, but without the parentheses, negative 2 squared like so, that would be equal to negative 4. That's because we do the exponents first and then the negative sign afterward. So in this case, you have to be a little bit careful. We have multiple solutions in this case. In this case, there are 2 solutions. And we'll find that for quadratic expressions and quadratic equations, we should expect 2 solutions. Although those 2 solutions may end up being the exact same number at times. And we'll see some instances where that's the case. The easiest case I can think of is x squared equals 0. Because there's only one number, which when you square it equals 0. That's 0. And I know what you're thinking, Professor, doesn't that mean there's only one solution to that equation? It depends on how you count it, right? The mathy type people will say that there are 2 solutions that are just the exact same solution appears twice. In general, I should expect 2 solutions to quadratic equations. We'll get back into the equations in a little bit, but before we get into that, I want to look a little bit more about why quadratics are special and get into all of the factoring methods that we'll use later on. Quadratic equations are nice because they are easily maximized or easily minimized. This is why we see them in our word problems more often than not. Imagine some function, right? I'm going to have it be a quadratic function, x squared, our simple one. But let me plug in a couple of different numbers for x. I've just picked 5 of them, the middle of my number line, negative 2, negative 1, 0, 1, and 2. But if I plug those things in, negative 2 is equal to negative 2 squared. Remember our parentheses. The parentheses, when we square it, is a positive 4, is negative 2 times negative 2, positive 4. And likewise on down the line, -1 squared is +1. 0 squared is 0. 1 squared is 1. And 2 squared is +4. Notice how it looks like whenever I square something in this function, I'll never get a negative number. And at least this x squared would have to have something else to go along with it. If I had x squared minus 5, then certainly all of these numbers would be. But that's not this function. Notice how the numbers seem to get smaller towards 0 as I get closer to the middle of my table, x equals 0. Then they go back out again. We don't do a whole lot of graphing in this class, but if I were to look at something like this in a graph, it would stop up here at 4, it would come down to 0, and then it would go back up to 4. If I continued, that pattern would go in both directions. You may have seen this shape before in an algebra class, and this is called the parabola shape. And we don't do a whole lot of graphing, but the important thing about it is this point right here at the bottom. If I had another parabola which was turned on its head, that would be the very top point, the maximum point. But in this one that I've drawn, it's a minimum point, the lowest point that you'll ever get on this parabola and from this function. And because of that, it comes in a lot of handy for our word problem, because we might say, well, what's the maximum amount of profit? You could see that's a quadratic, easy to find. What's the minimum amount of costs? Also easy to find because it's a quadratic. This maximum or minimum place is called the vertex. And we'll see how to find it, I think, a little bit later, if not next week. So we often see quadratics in our business applications for that reason. We don't go too far into the mathy theoretical side of them, but they end up being very useful. I've got to take a rather large sidebar here because to deal with quadratics, we necessarily have to deal with factoring. I can't get away from it. As a matter of fact, I'd like to talk about how to solve quadratic equations, but before I even get there, I need to talk about how to factor first, because factoring is going to be one of the major ways we solve quadratic equations. There's a little bit of vocabulary for us. We factor as a verb. So when I say to factor something, that means to write it as a set of factors. Oh, that's interesting. Write an expression. Of course, I can't spell. Write an expression as a set of factors. Notice how factors, in this case, this factor is a noun. That must mean I have to give you the definition of factor as a noun. Factor noun. Feel like a dictionary today. So a factor is something which is multiplied. And I know that seems a little silly, but it's true. You've probably already used this word to describe other things, maybe not variables, but if I said, what are the factors of 6? You might say, well, I know a couple of factors of 6. 1 times 6 is 6. These two things are the two factors of 6, because when I write them as two things being multiplied times one another, we call them factors. If you are more familiar with your math vocabulary, you might recognize the word that I use to describe answer of a multiplication is product. And so factors multiplied together to be a product. Not always 2, but in this case 2. Certainly the same product, 6, can be found with different factors, 2 times 3. And so this factoring verb process, right, will involve me taking something which is not written as multiplication, right? not multiplication there, it's addition, and writing it as multiplication. Interesting, interesting. So the only way I know that multiplication and addition work together is distribution. And factoring you can think of as undistribution. It's exactly the same process, only backwards. If I look at this example here at the top, 8x squared plus 4x, the easiest method of factoring is called the GCF method, or the greatest common factor. Probably should have written that out. Greatest common factor. You've probably used that word before. You've probably dealt with greatest common factor or two. The greatest common factor means I'm looking for the biggest number and the biggest variable set, which is a factor of all of the terms. Remember, terms mean things which are added or subtracted. So if I look at 8x squared, that's the first term, and 4x, that's the second term. Let's break down what the greatest common factor is. That's the biggest number and the biggest set of variables, which are a factor of each. Well, it looks like 4 is the greatest common factor number part. Yeah, 4 is a factor of 8, and 4 is a factor of 4. That makes it the greatest common factor. Also, I have some variables here because there are variables in common. X is a factor of x squared, and x is a factor of x. Now that seems a little bit wonky because, again, I don't know what the value of x is. But I do know that anything smaller, right? When I have x squared, right, I can go smaller in terms of my variable exponents because those are factors. Factors are smaller. I just can't go bigger. Bigger is multiple, right? This is not a greatest or least common multiple discussion, right? Multiples are bigger, factors are smaller. My GCF is 4x. What does that mean? I'm going to factor it out of every single term. 4 times what equals 8? 2. X times what is equal to x squared? X times x, x squared. And I can do a little mini check here. 4x times 2x is 8x squared. So I'm on the right track. That gives me the first term back. Notice how I've opened a set of parentheses here for distribution. Let's see, the second term is a little bit more challenging. So 4 times what is equal to 4? Well, that's 1. And x times what is equal to x? X times 1 is equal to x. I don't like seeing 1 times 1. I'm just going to write 1. Close the parentheses. Interesting, interesting. Notice how something which was 2 terms is now something with 1 term times something with 2 terms. Let me try this. I'm going to write it in blue. There are 2 terms here. And I've written it as something with 1 term times something with 2 terms. The result would give me back 2 terms if I did distribute it out and follow all of my exponent rules. But it often looks like factoring makes things longer rather than shorter. And that's okay. Factoring is going to be a very important process when we start solving equations because multiplication has some great properties which addition does not have, and we'll get to that. In general, factoring, it makes things easier to solve, although factoring itself may not always be the most easy process to deal with. So I'm always going to look for one of those greatest common factors every time I start doing my factoring. All of the other factoring methods that we'll look at are easier, right? When factoring problem you're dealing with is smaller. And so the factor or the GCF method will take out all of that GCF stuff first, leave you with something a little bit smaller. So if you do have to keep going, GCF will make things easier. All right, I've drawn a little picture here. Right? If you've ever seen an illustration like this, this would be how we might look at factoring geometrically. These bars and these squares, they represent algebraic values. Imagine this square, right, is x on one side and x on the other side. I know the area of a square is length times width. So x times x, the area of that square block is x squared. That's why the x squareds will be represented with the big squares. Likewise, the tall columns are x tall and 1 wide. I'll write the x squared underneath. That's x squared. So each column is an x. And here I've got 3 of them. X plus x gives me 3x. And each one of these little blocks is 1 on each side. So the little blocks are 1. So if I added all of these things together, I would have x squared plus 3x plus 2. And this is why this manipulative is often used in an algebra class to show this. And so what I can do is I can rearrange these pieces, the square, the 3 columns, and the 2 little blocks. I can rearrange them into a rectangle. And essentially that is me factoring, right? Because when it comes to a rectangle, then a rectangle has a length and a width that are multiplied together to find its area. So if I find a rectangle which also has x squared plus 3x plus 2 as its area, then I can read its length and its width as 2 factors of x squared plus 3x plus 2. Again, it seems crazy at first glance. Oh, I have my mouse over in the wrong place. I was wondering why my mouse was appearing in the middle. Take a look at the rectangle diagram on the right. You'll notice 2 things. I see x squared, the bigger, plus x plus x plus x. That's 3 little columns. One of them is turned on its side. Plus 1. The total area of this rectangle is x squared plus 3x plus 2. So all the pieces which came from the left side have been rearranged into a rectangle. But I also know when it comes to a rectangle, the area is the length times the width. What's the length of this rectangle? So on this side, that's, let's see, draw a little arrow here. Well, the length of this square was x, and the length of this little bitty bar is 1. So doesn't that mean the length of this rectangle is x plus 1? I'm only looking at it in one direction. Likewise, width of this rectangle highlighted in a different color. The long side of the column, that's x plus 1 plus 2. So the length of this rectangle, x plus 2. I've just put them in parentheses to make it a little easier for me to see. But the length times the width of this rectangle is x plus 1 times x plus 2. And so when I put this together with my innate knowledge of how rectangles work and how area works, I can see that the area of the rectangle is the same thing as all the pieces that I had before. Only now I've made it into a perfect rectangle, length times width. That must mean that x squared plus 3x plus 2 is equal to x plus 1 times x plus 2. Not a problem, you say, Professor. I've seen that before. I feel pretty confident about that. As a matter of fact, you really didn't need to tell me that at all, because I would have just done this with the old school FOIL method. I would have done x squared plus 2x plus x plus 2, and I would have combined my like terms because I'm a savvy algebra guy or gal, and I would have made x squared 3x plus 2. I would have been able to tell you that those two things are the same. But remember, right, the goal of factoring is not to go from the factors to the written out or expanded expression. It's to do exactly the opposite. To start with the expanded and go to the factors. So it's usually very easy to check your answer, although getting what the answer is might take a little bit of work. We'll go over a couple of different methods how to do it. Once we get it, we'll just distribute and find our answer, or check our answer. Let's see. Let's look at a small diversion inside of a diversion. I apologize for having to go a couple layers deep on this one. The main method that I'm going to use for factoring is called factor by grouping. And here I've taken the same thing that we looked at on the previous page, x squared plus 3x plus 2. Yeah, it should have been 2. I wrote it incorrectly in my setup. Shame on me. X squared plus 3x plus 2. And I've written it out as x squared plus 2x plus x plus 2. Notice that what used to be 3x, I instead have now written it as 2x plus x. And there's a very good reason I've done it that way. I haven't shown you how to do the same thing yet, but at least for now, hopefully you can agree with me that, okay, Professor, I see that 2x plus x is 3x. I don't really know why you've done it that way, or I don't even know how I could do it that way. But play with me for one moment, right? Follow me through the process. If I have something with 4 terms, then I can break it up into 2 groups of 2. That's the grouping part of the factor by grouping. So I'm going to write a couple of parentheses here just to keep my mind organized. And I would always put a plus sign in between. If that third term was negative, because sometimes it will be, if this one here is a negative, I will put the negative inside the parentheses and always put a plus sign outside. That's just me. I think it works better that way. But when I have 2 very small groups, I can talk about the GCF of each group. Let's see, inside my first group, these 2, the greatest common factor is, well, it doesn't look like there's a number because the first term doesn't even have a number. It's got that hidden 1. I don't know what goes with that. So, but I do see that it does have an x in common. Pull out an x. That would leave x times x is x squared. X times 2 is 2x. And so you can see all I'm doing there is a little bitty GCF. Right? These factoring methods build upon one another. And that's the first group written as a set of 2 factors. Let me worry about the second group now. I don't see a number which is in common between those 2. And I don't see any variables which are in common between those 2 either. It doesn't look like they have anything in common. What I'll say is that whenever there's no other factors in common, there is always a sort of default or last resort factor in common. You have to have some kind of GCF to make this work. It's just that if there is nothing else, the GCF is 1. I know that's kind of silly, right? Because anything times 1 is itself. 1 times x is x. 1 times 2, 2. And it seems a little silly to write this as 1 times x plus 2. You'll see why in just a moment. I will always write it with that 1 there, right? Some people will say, you don't really need that 1, professor, and they're not wrong. But if you don't write the 1, I think it's a little bit harder to see what's coming up, because now that I've got each one of my factors as GCF'd, and now I'm going to look at the bigger groups. Right? 2 terms now. Do you see a common factor for these 2 terms now? One that's on the left, oops, not the highlighter. One that's on the left and one that's on the right. I don't see any number parts that are the same, but I do see a big old set of parentheses, x plus 2, which is in common. X plus 2, the whole thing, is the common factor. I'm always going to write the common factor first. Some students will say, I'll write that one last. I'm always going to write it first. That's just a personal preference. X plus 2 times x gives me the first term, and x plus 2 times 1 gives me the second term. Now you see why I needed that 1. Right? If I didn't have this 1, I wouldn't have known what to leave there behind once I took out that big x plus 2. And just like before, I have x plus 2 times x plus 1, now written as a set of factors. Right? If you do this on your own and you already knew how to do this factor method, you might have gotten x plus 1 times x plus 2. Remember, anything can be written either way when it comes to multiplication. It means the same. The reason why I went through this process was that if we could find a way to break up that middle term, because remember, that used to be 3x in the middle there. If we could find some magic way to break up that middle term, then factor by grouping would be really easy. But how did I know to take 3x and write it as 2x plus x? Right? Why didn't I write it as 4x minus x? Didn't do that in this case. Maybe in a different problem I would, but not here. Why didn't I choose some other way to write 3x? It has everything to do with that rectangle picture we saw earlier. There's something about the way that these 2 little blocks, right, finish that rectangle, and they tell us everything about, right, what we're looking for. That is, I know that I'm looking for things which multiply together to be 2, right, because 2 is the number of little blocks that I have. Right? But I'm also looking for things which add together to be 3, because that's how many long columns that I have. So in this factoring, you would look up above it, x plus 1 times x plus 2. Everything just kind of worked out. I had the correct number of little blocks, 1 times 2, and I had the correct number of long blocks, 1 plus 2. So there's something really special about those numbers. We have to be able to write down sort of a method how to find them. And we do have one called the AC factoring method. The AC factoring method will always work for anything which looks like this. AX squared plus BX plus C. A, B, and C, in this case, are numbers, but A is not allowed to be 0. Remember, if A was equal to 0, that would be 0x squared, and then we wouldn't have a quadratic at all. It wouldn't make very much sense. A is not allowed to be 0, but it could be anything else. I'm going to set up a little puzzle for myself here. I'm looking for two numbers, right? These are the two numbers which I'll use in the factor by group method. I know that when I multiply these two numbers together, I should get 6. Oh, excuse me, I should get 2. I should get 2 because that's the number of little blocks that I have. In general, I call this the A times C number. And if there is a number in front of the x squared part, you'll have to multiply it there. And so in this case, it's 1 times 2, right? 1 times 2. But in more difficult problems, that number might be 3 or 4 or 5 or 8. I don't know. Whatever that number is, you multiply those two numbers to give 2. That's A times C. And those same two numbers have to add together to give me 3. This number always comes from the B position. So I'm looking to solve a system of equations. It's a very small one, hopefully a very simple one, but a system of equations nonetheless. As I look at this, I like to start with the multiply because there's only a certain number of ways I can multiply together and get 2. I don't want to involve fractions here. Really don't want to involve fractions. Really, there's only one way to do it if I want to stick to whole numbers. 2 times 1 is 2. And it just so happens that 2 plus 1 is 3. And it solves both of these equations at the same time. So that's why the numbers 2 and 1 were so important. Once I find these two numbers, I would go back to my original problem and use those two numbers to rewrite the middle term. Oops, not equal, plus 2. And if this looks exactly like where we started with the factor by grouping method, you are exactly right. That's the reason why we need the AC factoring method, which kind of flows into the grouping method. We need both of them together to work with a lot of these problems. I'm going to give myself a little bit more space here, and we'll practice one more, because I don't think I gave myself more space, but I know, yeah, give myself some more space. Let's try one. Let's do 2x squared minus 3x plus 5. Minus, yeah, there we go. Let's factor 2x squared minus 3x minus 5. I'm going to set up my little system of equations. I'm looking for two numbers which multiply together to be A times C. 2 times negative 5, negative 10. And those same two numbers need to be able to add together to give me negative 3. Remember, that's the B number. This came from the A times C. One is the B number. And if I can solve this little puzzle, then I can factor. If this little puzzle cannot be solved, and that will happen sometimes, that means that this cannot be factored. Let's see, the factors of 10 are 1 and 10. I've got negative 10, that could be negative 1 times 10, or negative 10 times 1. Neither one of those seem to work because when they add together, I don't get negative 3. So it's not 1 and 10. How about 2 and 5? That feels like it should. So 2 and 5 could be positive 2, negative 5, or negative 2, positive 5. I think negative 5 and positive 2 are the numbers that I'm looking for. Positive 2, 5, positive 2. Let's check. negative 5 times 2 is equal to negative 10. Okay. Negative 5 plus 2 is equal to negative 3. So that works out. Okay? These are the numbers which I'm looking for. And if I can do this problem, it means that I can always factor using the grouping method. Give myself some more space. I'm going to take my original problem, 2x squared minus 5x plus 2x minus 5. And I know what you're thinking. Professor, I see there were two 2's and two 5's. Why didn't you put the 2 with the 2 and the 5 with the 5? Hey, why don't you do 2x squared plus 2x minus 5x minus 5? You could have done it that way. A lot of students will choose to do it that way. The only reason I chose not to do it that way is because whenever I have a minus sign, right, I like that minus sign to be here instead of here. It just makes it a little bit easier when factoring GCF, taking care of the signs. But either way would be just the same. As a matter of fact, we'll get the same answer both ways. If you want to pause the video and work it out the other way, go ahead, feel free. In my first group, common factor is x. That leaves, I think, 2x. X times 2x is 2x squared minus 5. Yeah, x times negative 5 is negative 5x. And then remember what we said about the greatest common factor of last resort? I don't see one, not a number, not a variable. Plus 1, 2x, 5. A lot of people will forget that sort of greatest common factor of last resort. 2x minus 5 is the greatest common factor now. And now that I'm looking at the big problem, and what's left? X plus 1. This is now completely factored. Awesome. Right? The reason why I don't like the little rectangle blocks that we did earlier is that if we did those little rectangle blocks from earlier, I would have to make a difference between positive x and negative x. They do this a lot of times in the sets by making them two different colors. So I would instead have to write 2x squared, and then some of my x's would have to be positive x's on one side, and then some of my x's would have to be negative x's on the other side. And it would always work out like that. But like I said, I don't like the little algebra tiles, and that's what they're called if you want to look these things up online. If you like that rectangle picture, that was an algebra tile manipulative discussion. It doesn't work so well when you start to get into multiple x squareds, and it doesn't work so well when you have to deal with positive and negative numbers. So it's a useful manipulative, and it's a useful thing to look at. But we kind of have to grow beyond it sooner rather than later class. Awesome. All factored out. So when we do all these kind of factoring, right, why are we doing these factoring in the first place? Factoring is one and usually the first solution method for equations, quadratic equations that we have. Notice how because this quadratic equation, x squared plus 3x 2, has the x in two different places, I can't separate and isolate that x value the same way I would in a normal linear equation. I can't do it. So I can't use the regular minus 2 divided by 3 stuff that I could for a regular linear equation. I need to factor that. Rather than go through the full process, because we factored this thing several times before, I'm just going to go ahead and copy down my result we've gotten in several other instances. Now, you might be thinking, Professor, that doesn't look any easier at all. We go through the factoring process if it doesn't look any easier. And the thing we're about to take advantage of, I think is really amazing. Called the zero product property. You don't have to remember the math word for it, but I bet you already know what it means. The zero product property says that if two things multiply together and they equal zero, then one of them had to be zero to begin with. The only way to get zero out of a multiplication. I'm going to write that in math terms. So if two things multiply together to be zero, I'll show it as A times B. It can be anything. That means that, and this fancy arrow means it implies that A was zero or B was zero. Only way to get a zero is to start with a zero. That's what that's saying. And I know that's very mathy symbols, but that's what that's saying. The only way to get a zero is to start with a zero. Don't forget that we're using or in a very mathematical, logical way here. They could both be zero. Or covers that situation. You've probably heard jokes like that before. You know, I'd like pizza or a hamburger. Yes, please. Right, implying that I want both because the word or includes the possibility for both. I know many times that we informally use it to mean either or, but either or is a different logical idea. It means one and only one. Here, mathematically, it could mean or both of them. So I'm going to write it that way. So if these two things multiply to be zero, either this one is zero or this one is zero. And hey, look what comes out of there. Two very small linear equations come about. I know how to solve each one of those things. I do minus 2 tells me x equals -2. That's a solution. Or it's 1 minus 1. X equals -1. Now I have two solutions to this quadratic equation. And they all came from factoring. That's why factoring is going to be so important with quadratics. I know it seems like it's a lot to learn for one topic, but we'll do factoring more often than you think, right? It's a neat method to have in your back pocket. I know that not all students like to deal with factoring all the time because we're about to see another factoring which will work most of the time. And you'll say, oh, well, if I just memorize that one, then I'll never have to deal with factoring. Maybe, maybe. But I like factoring. It's one of those things that, yeah, it's a little bit more algebra. There's a few more algebra steps. But I think it's a really neat way to see and two things multiplying times each other. Take a small breather here and see if you can solve this one. 2x squared minus x plus 1 equals 1. You can pause the video here, but I'll wait for just a moment longer. See what you get. Now, I know it's tempting to look at this one and go straight into the factoring, everything on the left side. You probably would be able to factor this. X plus 1 times x minus 2. Very tempting. But if you did that, right, and I'm just going to skip over all the factoring because actually, I don't know if you'd be able to do that at all. The reason why I don't do that is because remember back up here in the zero product property, I had to have two things multiply together to be zero for that to work at all. So I wouldn't even try to factor this before I made it equal to zero. Let me subtract the 1 from both sides.
and make this equal to 0 before I even start thinking about factoring. And when I do, notice what happens. This is actually really neat. This is something I don't even need the AC factoring method for. I can go straight to GCF. This is kind of cool. So there's not a number, but I see x, my GCF, times 2x minus 1, it looks like. X times 2x is 2x squared. X times negative 1 is negative x. Now using the zero product property tells me that one of these things had to be 0. Yeah, equals 0 is one of the solutions right away. Plus 1 plus 1. Divide by 2. X equals 1/2. Oh yeah, there could be fraction solutions sometimes, and that's okay. We'll have to make our peace with fraction solution. 2 solutions. For quadratic equations, I always expect 2 solutions, just that sometimes they're the same number repeated twice. Pretty neat, huh? I like it. Again, let's take a breath. If you need to take a break, please do. And go straight into the quadratic formula, though. This is the other solution method that people work with that makes them question why factors are even necessary. If this were a college algebra class, we would spend the better part of a week figuring out what this formula is, figure out where it comes from, and why it's put together that way. But long story short is that any quadratic, which looks like this, x squared plus bx plus c equals 0 as an equation, as long as a does not equal 0, as long as a does not equal 0, then I can guarantee that this equation has 2 solutions, perhaps the same number, but 2 solutions. Even better, right? If you were in a college algebra class, we would go through the full algebraic process. I can find them. And I bet you've seen this before. It has 2 solutions. I'm going to write it both at the same time because it's a fraction. And it looks like this. The opposite of b plus or minus square root squared minus 4ac all over 2a. Those a, b, and c numbers came from up here, a, b, and c. They're always numbers. Even better, a is not allowed to be 0, right? Because you see on the bottom of my fraction, I've got 2 times a. Well, if a was 0, then the number on the bottom of this fraction would be 0. Can't have that. That's why I had to exclude a equals 0 from my considerations. But this is really 2 solutions, right? I use the plus or minus symbol to write it as one solution set, but the plus one solution, and the minus one is a different solution. The minus one will be farther to the left on the number line. The plus one will be farther to the right on the number line. That gives me 2 different solutions. And remember earlier when I was saying, oh, well, it might be the same number twice? It's because whatever this thing is, this square root shape in here, if that square root shape is equal to 0, then I'm plus or minusing the 0. It's the same thing twice. That's what happens when I have the same number twice. That square root part inside the dotted box, that equals. It can happen sometimes. I'm going to erase that really quickly because I want to go back and I want to do the example from earlier. 2x squared, was it? 2x squared minus x plus 1 equals 0. No, it was equal to 1. There we go. I'll go ahead and now subtract 1 from both sides. Just the same way I did before. This time I'm going to write a plus 0 very explicitly. You don't have to write plus 0 when you're doing it on your page or even on your exam. The only reason I wrote plus 0 because I wanted to show you very explicitly that A is 1, B is negative 1. There's a 1 hidden in there. There's minus 1. And C is 0. A is 2, B is negative 1, C is 0. Once I have those, I can plug them into my quadratic formula. Opposite of B, put in parentheses, plus or minus the square root B squared minus 4AC all over 2A. Just plugged in my numbers, A, B, and C. And if you heard me singing that to the tune of Pop Goes the Weasel, maybe you want to search on YouTube for Quadratic Formula Song. I'm sure there's a bunch of middle schoolers who their teachers made sing that song and uploaded them on the internet. They will be tortured forever with the song, just like I am tortured forever with the song. I'm not too sad about that, though, because it's my job is to do the formula. Makes me money, right? Ding. Now, if you could type all this into your calculator, you'd be good to go. Type it in there twice, once with a plus and once with a minus. But since I don't have my calculator handy, I've got to do this by hand, so to speak. Minus minus 1 is 1. Negative 1 squared is positive 1. 4 times 2 times 0 is 0. Times 2 is excuse me. All right. So this gives me 1 plus or minus square root of 1 all over 4. Because 1 minus 0 is 1. And the square root of 1 is 1. 1 plus or minus 1, 4. That gives me two different solutions. Split them out. 1 minus 1 over 4 and 1 plus 1 over 4. And on the left, call x equals solutions. 0 over 4, which is 0. The one on the right, 2 over 4, which reduces as a fraction to 1 over 2. We get the same two solutions that we got earlier from factoring. X equals 0 and x equals 1/2. I'm just going to scroll back to prove to myself this is the same two solutions from earlier. X equals 0, x equals 1/2. Whew. Mess up on camera. But you can always use this method as long as a is not 0. B could be 0, and as we just saw, C could certainly be 0, but A is not allowed to be 0. There's a lot of methods here, and hopefully you didn't watch all this in one go, because if you did, you're going to have to come back and rewatch this step at a time and work through it. But try it out. See what you like and what you don't like. And remember, you can always get to my notes here, this OneNote notebook that you see me drawing into. You can get to that from the Blackboard course under course content. I should have a link directly to it. So if I've been scrolling back and forth too fast for you to keep up and take notes on your own,
never fear, right? You'll always go back and you'll be able to watch it. You can kind of scroll with me. Thanks for coming in. I apologize if it took a little bit longer than I wanted. These are the basics of quadratic formulas. See you next week for live sessions.